This is the section on engine theory, part 1. There are five basic sections rather, to jet engines. You've drawn them, you've labeled them. Now we're going to talk just a little bit more about each one, as we're slowly getting an idea of what all these parts are doing. Then we're going to go into each one even more in detail in separate chapters later this term. A section on intakes and compressors, combustion chambers and turbines, and exhaust. In the meantime, what do inlets do? By the way, you can also call inlets intakes. An inlet and an intake are the same thing on the test. Those words are interchangeable. In the industry, those words are interchangeable. You can use either one. They're there to do three things. Inlets are there to control the angle of the air going into the engine, the speed or velocity of the air going into the engine, and the pressure of the air going into the engine, specifically going into the compressor. If the angle's not right, the blades won't hit the air at the right angle. The compressor blades could stall. The faster the velocity, we can use the intake to compress the air. We want the right speed and pressure, so that the intake has to be designed just right so the air hits the compressor blades at the right velocity and at their optimum pressure. The compressor is there, and it does a couple of things. It's there to increase pressure. Now watch out on the test. Don't say, what's a compressor there to do? The compressor is there to compress the air. That's not going to get you any credit. The static pressure is going to go up. If we have higher static pressures going into the combustor and burning, we'll have improved fuel economy, lower TSFC. If we have a greater number of molecules per unit of volume, say molecules per cubic inch, then we can get more power out of the engine. If we have more molecules of air, that means more molecules of oxygen. If we have more molecules of oxygen, that means we can squirt in more molecules of fuel in the combustor, and we can generate more power out of the same size engine. So increased pressure gives us improved fuel economy, lower TSFCs, and increased molecules per unit volume or per cubic inch gives us more power. The combustor. Now we talked about the combustor, the function of it. That is, how does it increase? If the purpose of having a combustor on the engine is to get the core gases increased in their velocities, how does it do it? Was in the last in Jet Propulsion 1, you did it by burning fuel. The burning fuel increased the temperature of the gases. The increase in temperature made the gases bounce around faster and expand. They couldn't expand forward into the high pressure. They can't expand sideways into the side of the engine. They could only expand aft towards the big old hole in the back of the engine we call the jet nozzle. And so that's the function. How does it do it? But this is the purpose. What is the purpose of having the combustor on the engine? And that's to increase velocity of gases. The turbine is there to extract energy. Now, most of the turbine is there to extract energy to drive the compressor. But as you may have noticed from previous drawings, the stick diagrams, we put in extra turbines to extract extra energy if we have a fan, if it's a turbo fan, if we have a prop, or if we have an output shaft. So not only can a turbine be used to extract energy to drive the compressor, especially since nobody's making turbojets anymore, that turbine is also going to have to extract energy to drive the fan, the propeller, or the shaft. And although we haven't drawn it yet in our stick diagrams, we're also going to need to extract energy to drive the accessory section. The accessory section is a gearbox that goes into the engine. I guess I could draw you a picture here. Huh? Let's say here's our stick diagram of our typical jet engine. We got compressor blades and such, and turbine blades. Of course, we have extra turbine blades and a combustion chamber, and the shaft that everything runs off of. We're going to gear another shaft that comes out of the engine, and it's going to go into an accessory gearbox. It's called an accessory gearbox because it runs accessories, and it's a box, and it's got lots of gears in it. And we can bolt lots of things to it. We can bolt a starter motor, we can bolt an electrical generator, we can bolt a hydraulic pump to it, we can bolt a fuel pump to it. On a Cessna 172 or a Seminole, they have accessory gearboxes on the back of the engine. If we've got the engine on a 172 or Seminole and the cylinders are sticking out on the side, this back chunk right here, this is the accessory section, and we can bolt a vacuum pump on it, we can bolt an engine-driven fuel pump, we can bolt the magnetos onto it. So if you look at the picture of a reciprocating engine, you're going to see things bolted onto the accessory section of it. But accessory sections on piston engines are usually on one end because the crankshaft inside the engine is going into the accessory section. Here we don't have a crankshaft, but we need to have the shaft, since we can't bolt it out here in the middle, things into the middle of the intake, and we typically don't bolt things out here, or the exhaust. I guess this is the exhaust side, and we typically don't bolt things in. I didn't do a good job putting an intake and an exhaust pipe on my engine. We don't typically bolt things inside of the airflow because it messes it up. So we tend to put, here's the cowling. So we tend to put the accessory section inside of the cowling, but on the outside of the engine. So this right here is the accessory section, and it's going to take horsepower, not very much, but it's going to take a little horsepower off of the engine to drive the accessory gearbox and air accessory section. And those two terms are synonymous. You can use them interchangeably in this class and in the aviation industry. Accessory section and accessory gearbox are the same thing. Also, the exhaust you'll notice it sounds a whole lot like the intake. It's there to control the angle, the speed, and the pressure of gases, but of course in this case, instead of controlling them going into the compressor or into the engine, it's there to control the angle, speed, and pressure of the gases leaving the exhaust pipe, leaving the jet nozzle. If it blows out sideways, it won't push us forward very much. We want the air to flow out straight. If we have the right combination and speed of pressure, if that constriction, that convergent duct is contracted or converging just the right amount, we'll get the right balance of speed and pressure to get the greatest amount of thrust. So I'm going to give you a hint. This question is going to be on the test. Fill in the blank. It'll say something like this. List the 5 basic sections of the engine, and then list the purpose or purposes of each. So there's a practice question in the blue pages for you. Now, this list right here are components or systems that you will find on every single turbine engine that's installed on a flying machine, whether it's the APU or the engine, a turbojet or turbofan that produces thrust, whether it's a turboprop that's bolted onto an airplane, or whether it's a turboshaft engine that drives helicopter transmission. These are things you're going to find on every single one of those engines. Hey, the accessory gearbox, accessory section, same thing. You got to have a place to hook up the starter motor. Almost all starters are geared into the accessory gearbox. The fuel control has to know how fast the engine is spinning, and since the accessory gearbox is spinning around to the engine, you can bolt the fuel control to the accessory gearbox, and it knows how fast the engine is spinning. The oil pump is going to have to be spun. Typically, it's in or bolted to the accessory gearbox. Hey, sounds like that accessory gearbox is pretty important. You're going to have a lubrication system. So far, nobody's made a jet engine that didn't have an oil system to pump cooling oil and lubricating oil around the bearings and the accessory gearbox. And if you've got a turboprop or a turboshaft engine, the gear reduction box also has oil pumping in it. Nobody's yet made one for a jet engine on an aircraft that doesn't use oil. You got to have instruments. I remember going to part of A300, Airbus A300 ground school, and they even had instruments on the APU. Now, granted, you had to call them up, and it didn't tell you. The computer was running the APU for you. The auxiliary power unit, they usually put that little jet engine in the tail of the airplane. Although on a 727, it's in the right-hand wing, just in front of the right main landing gear wheel well. And you can actually see if it's running. You can see a hole in the top of the right wing near the fuselage with hot gases coming out. In any case, that APU, that auxiliary power unit, even on a computer-controlled airplane like an A300, you could look at the instruments on it and see what the RPM it was spinning and what the exhaust gas temperature was. Ignition. You got to get the fuel on fire. You ever light a candle? It's really hard to get it lit unless you have some way to heat up the wick. Same thing with the jet engine. You have to have some way inside of the combustor to get that fuel burning. Now, once it gets burning, you can turn off the ignition, and we'll talk a whole lot about that when we get to the chapter on ignition. But you cannot just go up to the back of a turbine engine with a Bic lighter and, wave your finger around and say, and tell them to spin it up and then just light it from the back. You have to have an ignition system to catch the combustor, to get the combustion process going. So on the test, a good test question would be, name 7 of the 6 different required operating systems that you find on every single jet engine. Okay, that was just a joke. I wouldn't ask you to give me 7 out of 6. It would be 6 out of 6. This list here are systems or components that you might find on some, but not all jet engines. That is, these are not required for a jet engine to be a jet engine. These are not required to get an engine started, to keep a jet engine running on every single jet engine. These are things that might be on some, but don't have to be on a jet engine, such as an electrical generator. Now, the likelihood of you having a jet engine that doesn't have an electrical generator on it is extremely small, but if you could get the jet engine started and not even turn on the electrical generator, the engine would run fine. You don't have to have an electrical generator for a jet engine to work right. Same thing with a hydraulic pump. Although there's no switch in cockpits to turn off hydraulic pumps, you don't have to have one, and I'm sure there's probably a small helicopter or a small turboprop somewhere that doesn't have a hydraulic system, and so they don't have a hydraulic pump bolted to the jet engine, although it's very common to have hydraulic pumps running off of the accessory section. Of course, you only have a bypass duct if you're a turbofan, so that means there's 3 other kinds of jet engines that don't have bypass ducts. Cooling system. I'm going to talk about cooling more when I get into the lubrication, but when I say cooling system, I mean some system other than the air going through the engine that keeps the engine cool. Interestingly enough, if you take your typical turbojet, or we'll just say that this is an engine core of any kind of turbine engine, and there's our compressor blades, here's our turbines. I guess I'll put an extra turbine in there so we can drive something out the front. And so we've got air coming through, because this is core air. Well, the combustion chamber in here, only about 1/3 of the air, you know what, instead of saying 1/3, we'll say 30% of the air is burned inside of the combustion chamber. If we have combustion going on in here, go ahead, make that noise. If we have combustion going on in here, the air coming through the engine, some of it is going to go straight in and get burned up in the combustion process. But some of the air is going to go around the combustion process, and it's there to keep the engine cool, and this air is going to mix. Let's see. This air is going to mix, so by the time it gets to the turbine blades, it's cooled down. Essentially, that means that 70% of the core air is there for cooling. Whoops. So you don't need a separate cooling system. Typically, remember, this is optional systems here. You don't need a cooling system because it's inherent in the design of the engine. So next time you're in class, look around. All those jet engines out there, there is not, I think one of them has a cooling system. The other ones don't. You don't have to have a cooling system. Inlet or intake, anti-ice. You're going to find this on the vast majority of engine intakes. Here's our jet engine, compressor blades. One of these days I'll draw an engine backwards. And here's our cowling, and here's the intake coming in. And of course, we're probably going to have some kind of a bullet here. We're going to take bleed air off of the engine and route it through a duct to cool, or rather to heat up the intake, so the intake stays hot and the ice can't stick to it. And typically we'll route the air down to the bullet so the ice can't stick to it either. But if there's no icing and anti-icing didn't work, you'd be fine. So you don't actually have to have an intake anti-icing system. It's probably just a really good idea. Compressor anti-stall systems. We're going to talk about that a little bit when we get to compressors, and a lot when we get to the chapter on anti-stall. But those rotating blades are just subsonic airfoils that are increasing pressure and increasing number of molecules per cubic inch. They're subsonic airfoils. It's kind of like a 172 engine in that it only works within a certain range of angle of attack. If you exceed the critical angle of attack, you've probably never heard of that phrase, like on a private pilot written test by the FAA, how do you stall an airplane? By exceeding the critical angle of attack. You can stall the compressor blades. We'll talk a lot more about that when we get to it. But if you look around the room and in Building 54, none of those engines have compressor anti-stall systems. The big turbojet, it's too old. They hadn't invented anti-stall systems. And the other engines, they didn't think it was worth it. We'll talk a lot more about anti-stall systems when we get to that chapter. Afterburner. Unfortunately, most civilian airplanes don't have afterburners. The only one I'm thinking about was the Concorde, but it's not in service. Obviously, you can buy some ex-military planes. I know there's a company that's got 2 or 3 F-104s and a company that's got a couple of F-4 Phantoms, and obviously they have afterburners, but they weren't really intentionally designed as a civilian airplane. But you can, and of course, you can run the engine without an afterburner. That makes it an optional system. A reduction gearbox is only found on turboprops, always found on turboprops, and is it's only found on turboprops and turboshaft engines, but you're always going to find them on there because the engine spins so fast, but that output shaft driving the propeller or driving the transmission needs to spin slow. But if it's a turbojet or a turbofan, you don't have to have it. So technically, a reduction gearbox is an optional system for a jet engine. The same thing, of course, obviously, if you don't have a propeller, you don't need a propeller and a governor, something to control the propeller. So it's an optional system. You don't have to have a propeller or a propeller control to be a jet, to make a jet engine operate. And thrust reversers. I was a navigator and then bombardier on a B-52. We had nice, powerful engines. Heck, they had water injection, which we'll talk about when we get to thrust augmentation. But it didn't have thrust reversers like most airlines do. It had a drag chute. In fact, most jet fighters don't have thrust reversers. They have drag chutes. Interestingly enough, the Panavia Tornado has thrust reversers instead of a drag chute, and it has an afterburner. But you don't have to have thrust reversers. You don't have to use thrust reversers for them to work, for the jet engine to work. So we're going to call that an optional system. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So a sample test question might be name 11 of the 10 different optional systems that could be found on a jet engine. Okay, I'm just kidding. It'll just be 10 out of 10. Okay, now we're going to get into some nomenclature, some semantics, some industry standard terms, if you will, about thrust. Gross thrust, static thrust, rated thrust, and net thrust. First of all, gross thrust and static thrust are the same thing. There is no difference between gross thrust and static thrust, just the names. If somebody says gross thrust, they could have deleted the word gross and typed in static, and it would have been the same thing. The definition of gross thrust / the definition of static thrust is any thrust where the forward speed of the engine is 0. I'll say that again. The definition of gross thrust and static thrust is any thrust where the forward speed of the engine is 0. So you could be on the ground holding the brakes, the engine could be at idle, and I'm telling you, when jet engines are at idle, they're generating thrust. If the engine's not moving because you're holding the brakes, let's not worry about relative wind, okay? If the engine's not moving, then you're generating a static thrust or a gross thrust. And at idle, you're developing a thrust. So you're developing some kind of gross thrust, a certain amount of gross thrust, a certain amount of static thrust at idle. If you push the throttle forward, you're producing more thrust, but if the engine is still being held still, it's still a gross thrust. If you hold the brakes and push the power lever all the way up towards takeoff power, you're still developing a gross thrust. It's a whole lot of it, but it's still a static thrust because the engine's not moving. I'll get to rated thrust here shortly. Net thrust, on the other hand, the definition of net thrust is any thrust when the forward speed of the engine is greater than 0. Anytime the engine's moving forward, you're developing net thrust. I'll say it again. The definition of net thrust is any thrust when the forward speed of the engine is greater than 0. So if you notice the difference, you ever heard if you had a job, you notice your paycheck is less than what you made. How much you made was gross pay, and what you get to take home after taxes and giving the government a bunch of money is net pay. Net pay is always less than gross pay. Guess what? It's the same with types of jet engine thrust. Gross thrust is always going to be greater than net thrust. You got to understand one of the ways you can develop thrust, and here I'm going to add a little number, F sub n is net thrust. So net force, net thrust. There's a lot of parts to it, but one of it is it's the mass times that change in velocity, which could be rewritten mass times velocity 2 minus velocity 1, where if here's our jet engine, air's coming in the intake, air's going out the tailpipe. We got a bunch of compressor blades, some turbines, blah, blah, blah. V1 is the forward speed of the airplane. Essentially, V1 is the airspeed of the airplane, and V2 is the velocity of the gases. The difference between the gases is the acceleration. That's the same as saying force equals mass times acceleration. Acceleration is the change of velocity. The velocities we're talking about is V2 minus V1. V2 is the exhaust. V1 is the intake. So we're always going to be subtracting V1. The greater V1 gets, the difference here is less. So we multiply less times mass and we get less thrust. So if we're moving forward, we're going to get a little bit less thrust because we didn't accelerate the air as much. But if V1 equals 0, then we have F sub g, or gross thrust, because the value of V1 is 0, and the definition of gross thrust is any thrust where the forward speed of the engine is 0. Anytime the forward speed of the engine is greater than 0, then this number here is going to get smaller, and that's going to cause this F here to get smaller. Okay, so now we know what net thrust is. Back to rated thrust. Another way to call rated thrust is red line power. Whether it's EPR, RPM, torque. It's also going to be the FAA maximum under non-emergencies. Of course, if it's a real emergency, you can go past the red line, but we'll talk about that later. Emergencies. It's red line, it's FAA max, and it's the highest power setting you can get. Highest power under non-emergencies. And guess what? You know what? These, let's cross this one out. Let's just call it like that. There we go. And it's always written as a gross thrust or static thrust, because those are both the same. So we'll say that there's three characteristics that define rated thrust. It's the red line power setting, which we all know about red lines on gauges. It's also the FAA maximum approved power you can use under normal conditions, and it's always rated in a gross thrust. Hey, if you're going to advertise an engine and you're going to say how much thrust it gets, you're not going to give out the net thrust at cruise, because that's not as big as the gross thrust or static thrust when the engine's not moving. Okay, thrust versus horsepower. Now, thrust is a force, and we're going to do all of our force calculations in this course this semester. We're going to do all those thrusts in pounds of force. Horsepower, however, that's what HP stands for, horsepower, is a force, but you multiply it by distance divided by time. And of course, for instance, miles per hour, miles per hour, you'll notice it's a distance divided by time. Distance divided by time. So, I could even do that. There we go. So, miles per hour, or velocity, this right here, is the same as velocity. And of course, instead of doing miles per hour, we could do knots, true airspeed, or knots, indicated airspeed. So, horsepower is force times velocity. Or we're pilots, so we're going to say, we could say force times knots if we wanted to. Well, guess what? Let's say you're sitting at the end of the runway, and you're in this big old jet airplane, and you got some couple of jets on the back. Let's say you're an MD-80 series, and here's the cockpit, and you're inside going, yay! And you got the throttles going, but the forward speed of the airplane is 0. So the knots equals 0. What's the horsepower being used up by the airframe? Well, you'd have a lot of force. You could have tons of thrust. You could have tons of thrust, tons of force trying to push the airplane forward. But if you're holding the brakes, or you're tied down with the chain, you can have lots and lots of force. This number here could be really, really high, but your velocity, the distance you're covering, is 0. So guess what? Knots are 0. Any kind of force times 0, that's going to equal 0 horsepower. So the airframe's not going to be using any horsepower unless you're moving. But if you let go of the brakes, oops, there went my runway. We're falling out of the sky. Oh, sorry. If we let go of the brakes and we start moving, and now the velocity in knots, or our distance covered per time period, is going up, then horsepower being used up by the airframe is going to increase. So the faster we go, the more horsepower gets used up by the airframe. Well, essentially this means that using horsepower to compare engines from one engine to another doesn't work out very well, because it depends on how fast you're going. You could take an engine and put it on an airplane that goes 500 knots, and it would be giving a certain amount of horsepower to the airplane, but you could put it on a different airplane that does 550 knots, the exact same engine, producing the exact same force, the exact same thrust, but you'd come up with a different horsepower. So you really can't use horsepower versus horsepower to compare turbofans and turbojets. And I already answered that question. Okay, turboshaft and turboprop horsepower are both measured in, well, the first one, and let me rephrase that, turboshaft engines are measured in shaft horsepower. Remember, we got that output shaft. See how well I can draw this. Some extra turbines to drive the output shaft. I'm not doing a very good job. Hopefully you remember from last time. Yeah, these need to be a little bigger here. In any case, it's how much shaft horsepower goes to that output shaft. That's what we're worried about in turboshaft engines. Now this 2.5, it's a constant, but it's an imperfect. That is, it's a not perfect constant, because every engine is a little different. It also varies by what forward speed you are, but it's a reasonable number if we wanted to compare things. We could take, if we got rid of, for instance, if we got rid of this output shaft, and we just said, hey, and and let's get rid of the turbines that were driving it, and we just had gross thrust coming out of that engine, and we go, you know what if we put a gear reduction box on it and an output shaft? What would we expect to get out of it? If we had, say, a 1,000 pounds gross thrust engine, 1,000 pounds of gross thrust over 2.5, that would tell us the shaft horsepower. Let's see, 25 goes into 100, 4 times 40, 400. So this ought to be, am I doing this right? This ought to be 400 shaft horsepower. So then this is a very approximate kind of a number. If we took a turbojet and then put in some turbines, I forgot the turbines, to drive the output shaft in the gear reduction box, and it used to have 1,000 pounds of thrust as a jet, we could expect to get about 400 shaft horsepower out of it if we put some turbines in it and converted it into a turboshaft engine. Now, turboprops, on the other hand, are a little bit different. Turboshaft engines, remember, we are saying that there's, for practical purpose, we don't pay any attention to or the fact that they don't develop thrust. However, turboprops, we are going to take into account the fact that there is some thrust from the engine. This shaft horsepower right here is the shaft horsepower going to the propeller, and this gross thrust is coming out of the exhaust. So if we had a turboprop down here, let's see how well I can do this time. We've got compressors, and we've got the turbines to drive the compressor. Let's put a couple extra turbines in so we can drive the propeller. I'll make a nice big propeller out here. And of course, we've got to have the combustion chamber. I'm not doing that good drawing my intakes and my exhausts this term. Okay, we're going to get some thrust. We're going to get some thrust off of the prop, and we're going to get some thrust off of the engine core. And if you recall, 90% of the thrust is going to come from the prop, and 10% of the thrust is going to come from the core. And this 10% is important. We want to develop thrust. We're going to take that into account. So this gross thrust divided by 2.5, that's going to help us determine how much of the thrust is from the core, except instead of converting things into converting stuff and leaving it as thrust, we're going to take this gross thrust, divide it by 2.5, and convert it into, effectively, what's this power worth in shaft horsepower. And then we're going to add that worth of power in shaft horsepower to the shaft horsepower that's going to the prop, and that's going to give us equivalent shaft horsepower. Equivalent shaft horsepower. So let's just say we got a turboprop. Make sure we put the extra turbines in there. And we're spewing out 250 pounds of thrust out of the core, and the power going to the propeller shaft is, let's say, 900 shaft horsepower. So we can plug the numbers in. 900 shaft horsepower going to the prop. Gross thrust of the core is 250, and we got to divide it by 205. So we get 900 plus, let's see, 2.5 goes in, 100. So we've got 1,000 equivalent shaft horsepower. And in turboprops, that's how you compare one turboprop to the other. All turboprops are calibrated or rated in equivalent shaft horsepower. Remember, rated power, that's the red line. That red line power is always going to be an equivalent shaft horsepower. It's going to take into account the thrust produced by the exhaust and add it, that power being put out by the propeller, and we're just converting the exhaust thrust into the equivalent of shaft horsepower. So you ought to be able to do the homework questions now pretty easily. This formula right here, I'm going to give you on the test. This formula right here, I'm going to give you on the test. Except I think what I'll do, I'll call this GRGT, and I'll call this one right here, I'll call this GT. You'll just have to remember that this is shaft horsepower for the propeller, and this is the gross thrust for the core. How's that? Go practice the homework. Bypass ratio. I've covered bypass ratio a little bit before. I just want to make sure I get it. Well, it's a ratio of mass, a ratio of weight, if you will, of how much air is going through the bypass versus how much air is going through the engine core. So if I draw a duct and a nice big ol' honking fan, and here's my engine core, and some turbines to drive the compressor, maybe a turbine or two to drive the fan. I need a bunch of compressor blades, and here's a combustion chamber, and we're going to have core airflow going through the fan, but right now we're just worried about the fact that it's going through the engine, and we're certainly going to get pounds of air. You notice this is not thrust. We're not talking about thrust. Thrust here is about 9 to 1, 90% versus 10%. And then, of course, we're going to have the bypass airflow. And that, I remember I told you that 747-100, 1969 was it went into service. That those Pratt & Whitney JT9Ds had a 4-to-1 bypass ratio. The 777, the first model that came out, one of the engines you could get on it was a GE90. It had a 7-to-1 bypass ratio. If you've ever heard of a 727, the very first ones that came out, it had a 0.8 to 1. That is, it had a really small bypass ratio. The fan wasn't very big. In fact, it looked like the engine was skinny. If you look at the really old 737s, the Dash 100s, Dash 200s, maybe even the Dash 300s, the engines looked pretty skinny, and it was because the bypass was so small, it looked like a turbojet. And they all had the same engine, that 727 and those early 737s, that had a Pratt & Whitney JT8D that had a very low bypass ratio. This first number is the bypass. How much air in pounds per second are going through the bypass. And the second number is pounds of air going through the core. So we could say that the formula would be bypass ratio equals the bypass air over the core. And this is pounds of air. It's not thrust. It's not pressure. It's not volume. Oops. It's pounds. And you ought to be able to solve. I mean, I can try to do one of these. If you can't do ratios, please come see me. Seriously, I'd be happy to show you how to do it. If you can do the problems in the blue pages, this formula, bypass ratio equals bypass over core. I'm going to give you this formula on the test so you can do one or two of these problems on the test. And no, you don't have to do any math problems on the quizzes. Net thrust for a turbojet. Okay, here's the net thrust. On the test, you're going to need to know what each of these variables are. F sub n is thrust, comma net, or net thrust. Gross thrust would be F sub g. But most of the time in airplanes and jets, we're worried about how much thrust there is when the engine is moving. If the engine's not moving, we're not flying. So F sub n is what we're going to be thinking about the vast majority of the time. WA is the weight of the air that the engine is acting upon. If it's a turbojet, for instance, then only the core air is getting acted upon by the engine because there's only an engine core. So the core airflow would be equal to WA in a turbojet. G is the force due to the acceleration of gravity, and that's 32.2 feet per second. I'll be happy if you remember it's 32. I'm not going to tell you that G is 32 on the test. V2 is the second velocity that we're concerned about. That's the velocity coming out of the exhaust. And V1 is the velocity of the air entering the engine. The other way you could describe V1 is the forward speed of the aircraft. WF is the weight of the fuel. We're going to squirt some fuel in here out of some fuel nozzles, and we're going to burn fuel. Well, this weight this mass gets accelerated. So WF over G is mass, WA over G is mass, and then of course V2 minus V1 is the change in velocity. Now here, VF, why don't we have VF2 minus VF1, is because VF1 is always going to be 0. The relative speed of the fuel when it enters the engine is 0 knots, or 0 feet per second. So this, you could have written this W sub F over G times VF2 minus VF1, but VF1 is always going to be equal to 0. So anything minus 0 is itself. So let's just forget about that completely. It's going to be WF times V2 over G. Oh wait, VF2, interestingly enough, VF, these molecules of fuel, and of course when we combust them, they're going to change into different molecules. They get accelerated to the exact same speed as the rest of the air that came into the engine in the first place. So V2 is always going to be the same as VF, or vice versa. VF is always going to be the same as V2. So if you know what V2 is, you know what VF is. So this is a mass times a change in velocity for the air going through the engine, and this is the mass times change in velocity of the fuel. So we've got to take into account that. Now this is going to be a really small number, but that's all right. Then of course we have area of the jet. We've already done area of the jet times the change in pressure, and of course the pressure is going to be pressure in the jet. We're talking about P sub J, that's pressure in the jet nozzle, versus pressure ambient. If the ambient pressure out here is 14 psi, well, we'll call it 14.73 psi, and the pressure in here is 24.73 psi, then that's going to give us a difference. This number right here is going to end up being 10, and then of course we multiply it by the area of the jet nozzle. So that's what all of those factors are. We're going to try doing a sample problem. It's required by the university, and people want to know how jets work, so I'm going to show you. Okay, let's do a sample problem. In the Traeger textbook, on page 143, there's a sample problem, and I changed some of the parameters a little bit to make it a little easier, a little more understandable, hopefully. And we're going to use this set of data here to plug into the net thrust formula. So 2,200 pounds per square feet ambient. If we divided that by 144, we'd get pounds per square inch. And this 2,200 divided by 144 is going to be 14 point something or other pounds per square inch. It's not going to be exactly 14.73, so it's close to sea level. This 450 feet per second true airspeed, well, 1,100 feet per second is 662 knots true airspeed. So 450 feet per second true airspeed, that's a little bit less than half of 1,100. So this is probably doing about 300 knots true. 96 pounds per second inlet airflow, that's how much air is going through the core of the engine. We're just doing this sample problem here is going to be on a turbojet. We'll worry about turbofans and turboprops here shortly. 2 square feet on the area of the jet nozzle. So if we've got a jet engine, that's essentially the area of the exhaust. 5,600 pounds per square feet in the jet nozzle pressure. So the pressure in here, that's pressure in the jet. 5,600 pounds. Wow. If 2,200 is about 14, 5,600 is about 2.5 or 3 times bigger than that. So maybe that's 2.5 or 3 times 14. So 30 or 40 psi, pounds per square inch. 1,450 feet per second exhaust velocity. That's V2. So that's V2. That's the exhaust velocity. Well, if 1,100 feet per second is 662 knots, then that means this is about a third again as big. So a third again as big, that's going to be a couple of hundred. So maybe that's going to be about 800 knots to airspeed. And 1 pound per second fuel flow. Now in airplanes, if we typically on jet engines, we look at pounds per hour, not pounds per second. So 1 pound per second, we'd have to multiply this times 3,600 because there's 3,600 seconds in an hour. So we might get like something, I don't know what that is, like what's 36 times 1.5? Like 5,000 pounds per hour, but we're not going to worry about doing those calculations. So this right here is the weight of the fuel. Right here, this 96 pounds here, that's weight of the air. 450 knots second true airspeed, that's our velocity 1, V1, that's the speed of the air coming in the engine. Here's ambient air pressure. So this is going to be pressure ambient. And what did we get here? Here's pressure in the jet. So I guess we've got, oh yeah, and G equals 32.2. Remember, I'm not going to tell you that on the test. So let's try doing this example here. Start with the formula. Well, I probably could go slide back or two. I wouldn't have to write that over again. Dun, dun. Here we go. If we put these numbers in, net thrust. So here's pounds of net thrust is what this is. F is for force, N is for net. So weight of the air was, maybe I need to do it this way. Weight of the air is, oh, I got this written down. Here we go. Weight of the air is 96 pounds per second. V2, which is the velocity of the air leaving the engine, is 1,450. V1, or the speed of the air coming into the engine, is 450. And of course, gravity is 32.2. So this right here, that's going to be essentially mass times change in velocity of the air. So here is going to be mass times change in velocity. Of course, this is going to be velocity of the fuel. So we're going to bring this plus sign down here. Weight of the fuel is 1.6 pounds per second. And VF is the same as V2 because all the fuel molecules, even after they get burned in the combustion process, are going to get speeded up to that same exhaust velocity. So VF and V2 are the same. And of course, we've got to turn this into mass, so we have to divide by acceleration due to gravity, which is 32.2 feet per second. Okay, we'll bring this plus sign down here. And area of the jet nozzle. The area of the jet nozzle is 2 square feet. And we're going to multiply that by the pressure in the jet, the pressure in the tailpipe, which is 5,600 pounds per square foot, and then we're going to subtract the ambient pressure, which is 2,200. Now remember, on the test, you're not going to be allowed to use a calculator, so you're going to have to do this in long division. So here we go. Next thing, I'm going to start simplifying each of these going down. So I'm going to go 96, 1450 minus 450. Wow, that one's nice and easy. So there's 1,000 over 32.2. And 1.6 times 1450. So I recommend that you WAG these things. So 1.5 times 1500 is going to be 1500 plus 750. That's about 2250. So the answer here ought to be about 2250 or something like that. And so you can go somewhere. I know this is terrible doing long division. 6 times 0 is 0. 30, carry the 3, 24, 27, carry the 2, 6, 7, 8. 8,700. That doesn't look like I did it right, did it? Oh, wait. Now I got to do the 1. That's 6. 1 times 0 is 0. 1 times 5 is 5. 1 times 4 is 4. 1 times 1 is 1. 0, 0, 12. Carry the 1, 9, 13. Carry the 2. Oh, wait, and this decimal place is over here. So since we have, it's 1 decimal spot over, we got to move this 1 decimal in. 2320, which is really close to my WAG at 2250. So yay, I probably did it right. 2320 over 32.2. And so here I'm going to WAG this. 56. 5 minus 2 is 3. So I had to get an answer somewhere around 3,000. This one's pretty tough. 5,600 minus 2,200. And sure enough, it is 34,000. Wow, I bet you I could do that. 3,400 is almost 3,500. 35 times 2 would be 70. So the answer here ought to be a little bit less than 7,000. In fact, it ought to be 200 less than 7,000. This ought to be 6,800. You have to let me know see if I did that right. 2300 divided by 32. Well, let's see. This decimal is lining up right here, so it's really close to 32 and a 2300. If we not shaved this off right here, it'd be 3 goes into 232. Well, 3 goes into 2100 70 times. So my answer here ought to be somewhere around 70. See how I'm estimating or wagging it? So I'll use my long division here. 32.2 goes into 2320. Okay, I'm going to move the decimal over. Move the decimal over, so the decimal is going to go right here. So now 322, it won't go into 232, but 322 will go into 2300, probably about 7 times. So 7 times 2 is 14, carry the 1. 2 times 7 is 14, plus 1 is 15. Carry the 1. 3 times 7 is 21, plus 1 is 22. When was the last time you did long division? Let's see, 10 minus 4 is 6, 1 minus 5. Oh, can't do that. Turn that into a 2. Bring the 1 over. 11 minus 5 is 6. 2 minus 2 is 0. Sweet. And 0 here. Great. So now I can drop the 0. Go 0 here. 322 goes into 660. Wow, almost exactly 2 times. Sweet. So 2 times 2 is 4. Don't have to carry. 2 times 2 is 4. 2 times 3 is 6. Let's see. That turns into 5. 10 minus 6. 5 minus 1. Drop to 0. Won't even go into it once, so it's going to be 0. You know what? And let's see if we drop another 0 down. 322 goes into 1600 about 5 times. Dun, dun, dun. And I'm going to say that's close enough. So down here, I'm going to say, let's just round to the nearest decimal. Let's just round to the nearest decimal. So we're going to say this is 72.1. That's good enough for me. Now, 96 times 1,000, that one's going to be pretty easy. So this is going to be 96,000 over 32.2. And again, if I moved this decimal over and I moved this decimal over to here, then it'd be the same as 322 goes into 960,000. Or we could just kind of get rid of this for a second and get rid of this. And it's 3 into 9,600. Wow, 3 into 9,000. 3 goes into 9,000 3,000 times. So it's going to be a little bit higher than 3,000 ought to be. That's my estimate for here. So let's see if I can find. I'll have to erase some stuff up here. Give myself some room to do some long division. Woohoo! Long division. I remember long division. I think it was the 3rd grade. When was the last time? I already asked that question. Never mind. My eraser is not working as well as I want it to. Remember, get a good eraser for the tests, because on those Scantrons, you need to be able to do it well. All right, so back to the felt tip pen. So we have 32.2 into 9600. And we're going to move this decimal over, so we'll move this decimal over. Here's the decimal. Here's the decimal. So 322, it'll go into 960. Probably not quite 3 times. Just for fun, we'll try 3 times. 2 times 3 is 6. 6 and 9. 966. Oh, man, that's almost 3. Darn. So it'll go into it twice. 2 times 2 is 4. 2 times 2 is 4. 2 times 3 is 6. Drop to 0. This won't go into it 8 times, 9, 10 times, maybe 9 times, just for fun. Okay, 32.2 times 9. 2 times 9 is 18. Carry the 1. 18 plus 1 is 19. Carry the 1. 7, 28. 28. Sweet. So do it 9. 2, 8, 9, 8. 15 minus 9 is 6. Am I doing this right? 0 minus 8, 2, 10, 2. 262. Drop the 0. 322 goes into 2600. 3 goes into 26. 7 would be 21, so it's probably about 8 times. So let's try 8. Yeah, it won't do it 9 times. 8 times. 8 times 2. 16, carry the 1, 16 plus 1 is 17, carry the 1, 3 times 8 is 24, 25. Do you talk out loud when you're doing math? If you need to fast forward it, that's cool. Okay, 44, drop the 0. Remember, we're just looking for this last rounding it to the nearest decimal. It'll do it once. 322. 108 and drop to 0. Down. That'll do it about 3 times. So we're going to round this to 298.1. That doesn't look right because we ought to be having about 3,000. So it looks like I messed up my decimal someplace. 298. It's because it was 96,000 and I didn't have enough zeros here to start with. Should have had a 0 and gone over to here. There we go. It's a good thing I did this this estimate here. It's really 2,981.3. We'll say that's close enough. 2,981.3 plus 72.1 plus 6,000. So that one's going to be really hard. So we ought to be looking at about 9,006 plus almost 3,000 is 9,000, and this isn't very much. So the answer here ought to be about 9,000 and some. Just for fun, we'll just go ahead and do that. 6,000, 2,981.3, and 72.1. 9,053. So 9,053.4. And you got to label it. You got to label it. You got to label it. Pounds of net thrust. And if you'd rather use LBS, that's cool. That's an industry standard term, LBS, pounds of net thrust. So I just recorded this. I hope I came up with the right answer. This is the difficulty level of what you're going to have to be able to do on the homework and what you're going to have to be able to do on the test. Remember, do this, practice it without a calculator, and just round each of these numbers to the nearest decimal place, and that'll be plenty accurate. If this is for a turbojet, how do we change this formula to turn it into a turbofan? Well, this part right here, now that's for the engine core. If we have a turbofan, now we have thrust from the core. So this takes care of the core, but we got this bypass air that we have to take into account. So if this formula right here takes care of the engine core, then we're going to have to add in the weight of the air from the bypass over gravity times the accelerated velocity of the bypass minus the inlet velocity of the bypass, which of course these two are going to be the same. And we're not squirting any fuel into the bypass, so we don't have to worry about fuel. So we just have to worry about the area of the jet nozzle of the bypass, which would be this area right there, minus the core, of course, times pressure in the jet nozzle of the bypass, minus pressure ambient coming into the bypass. And, of course, the ambient pressure going into the engine core and going into the fan are the same. So this part right here, one could say this is the thrust for the fan, or you could say F sub N fan if you wanted, and you could call this F sub N core. So it's not too bad. It's the same thing. We got to worry about what are we accelerating, and since we don't have any fuel in the fan, we don't have to do it again. And how did we change the pressure? If we want, so that would turn it into net thrust for a turbofan. Now, if we wanted to turn this into net thrust for a turboprop, it's essentially identical. If we wanted to do net thrust for a turboprop, whoops. I got to turn this into a turboprop. Got to have our little reduction gearbox, and we got to have a propeller. Okay, the core is still going to be the same. Here is the thrust from the engine core, but we're also going to have this bypass air going through the propeller. So we could say that we need to make sure that we take into account the weight from the prop, the mass of the prop, weight over gravity is prop, velocity 2 of the prop, which is going to be different than the engine core, but velocity 1, the air coming into the propeller, is going to be the same if it goes through the core or if it goes through the prop, so V1 is still going to be the same. We're not going to squirt any fuel in here after the propeller to burn it, so we do not have to take into account burning more fuel. And it's the area of the jet of the prop. We have to take into account this area of the prop disc, which is going to be a lot bigger than it was on a turbofan. Pressure of the jet for the prop. So that's the pressure on the back side here. That's pressure, the jet of the prop. And of course, ambient, again, out in front of the air engine, in front of the propeller, the air pressure going into the engine and the air pressure going into the propeller are the same. So now, this would give us the thrust for the propeller. Or it would be net thrust of the prop, and we'd still have to add that. See, we still got to add that to the net thrust of the propeller. So the net thrust formula for a turbofan and the net thrust formula for a turboprop are essentially the same. You still need to take into account the weight of the air, the weight of the fuel, and the differential pressure for the engine core, just like you did on a turbojet. But now you have to take into account the mass of air that's being accelerated by the fan or the prop, and the pressure differential across between the two sides of the fan or the two sides of the propeller. I'm not, on the test, going to give you a problem where you have to calculate net thrust for a turboprop or a turbofan. It's only going to be as per the example I did a couple of minutes ago, which is the same as the practice questions, the practice net thrust formula questions in the blue pages. We're only going to do, for mathematical calculations, net thrust for a turbojet. So we changed it to here's one. How could we change it to gross